Good morning, my dear friends. I hope you all are doing great. Dear friends, today we'll be talking about solid vapor equilibrium. Okay, let's have a look, my dear friends. This is iodine solid. Let's take an example. Iodine solid is kept in a closed vessel. Okay? Iodine solid has a property to undergo sublimation. Sublimation means it will change into the vapor state, correct? As iodine solid starts changing into iodine vapors, okay? So during sublimation, iodine solid is changing into iodine vapors. The intensity of violet color, and remember this violet color is because of the iodine vapors. Look here, as iodine solid starts changing into iodine vapors, the intensity of violet color in closed vessel increases. So intensity of the violet color will increase because your iodine solid is changing into the iodine vapors, and because of the iodine vapors, the inside the container the violet color intensity will increase, my dear friends. Okay, then what happens? Finally, the violet color intensity becomes constant. What was happening? Iodine solid was changing into iodine vapors, and because of these iodine vapors, the intensity of violet color in closed vessel increases. But finally the violet color intensity becomes constant. First of all, violet color intensity was increasing as iodine solid was changing into iodine vapors. And ultimately what happened? Now the intensity of violet color is not increasing, it has become constant. Reason is the equilibrium, my dear friends. So finally the violet color intensity becomes constant, which means, okay, system, or we can say that, which means equilibrium has been achieved. Which means equilibrium has been attained by the system. Correct? Now have a look, my dear friends. Let's take on a closed vessel here, and let's take some iodine here. So this is closed vessel, because for equilibrium we need a closed system, remember that? And this is our iodine solid, my dear friends. And this iodine solid will undergo sublimation, means it will change directly into the vapor state. So we will have here, this is our iodine vapors. So my dear friends, what happens before equilibrium? Try to look. Before equilibrium, what happens? Iodine solid, okay, was changing into iodine vapors, okay, and they will have a violet color. So violet color was increasing, okay. So here the violet color was increasing as violet color intensity increases due to the formation of iodine vapors. Okay, so this is before equilibrium. So what happens at equilibrium? my dear friends, you have here iodine solid. Here only sublimation was taking place before equilibrium. And now at equilibrium, iodine solid will undergo sublimation. Okay? And it will change into iodine vapor. And here the iodine vapor will change back into the iodine solid. That is deposition. So deposition will happen. Iodine vapor will change back into iodine solid. So remember, iodine solid is changing into vapor. Then vapor is changing back into the solid. So color will remain constant. So here I will tell violet color intensity remains constant at equilibrium, my dear friends. At equilibrium. The reason is simple, because solid is changing into vapor and vapor is changing back into the solid. So color will remain, the intensity of color will remain the same, no change. So this is at equilibrium what is happening. So my dear friends, now overall you have understood everything right out here, my dear friends. So finally you can put it like this: iodine, this is vapor, this is our solid. So solid is changing into vapor. So I will write down rate of sublimation, okay, is equal to rate of the iodine vapor is changing back into solid. That's called as deposition. So my dear friends, rate of sublimation is equal to rate of deposition, okay, at equilibrium. The meaning is very simple. The speed or the rate or the velocity with which solid is changing into vapor, with the same speed or same velocity, vapor will change back into the solid. That's why I'm writing rate of sublimation is equal to rate of deposition at equilibrium. And you also know that at equilibrium, delta G is what? 0 obviously. So at equilibrium also, our delta G for this process will become 0. Give us free energy change will be 0. I hope you have understood this particular thing very well, and you can take example of other substances also, and you can take them in closed system, and they will also show the same process, and they will also reach to the equilibrium. Beginning, sublimation will happen. Finally, at equilibrium what will happen? Sublimation will become equal to deposition. Forward process will become equal to backward process, and delta G will become equal to 0. Even you can take other examples as well. You can take an example of here, my dear friends. So other examples you can take, like you can take camphor solid. Okay, it will change into camphor vapor. Okay, so I am talking about these processes at equilibrium, not before equilibrium. So we are talking about these processes at equilibrium. Or you can take ammonium chloride solid, and then it will become ammonium chloride vapors. Yes or no? At equilibrium in closed system or closed vessel, you can say. And here also we know that delta G is equal to 0, my dear friends. So this is your sublimation and this is your deposition. So these are the other examples for solid vapor equilibrium, my dear friends. Please make note of this. Now let us understand solute-solid equilibrium. This is also called as equilibrium involving dissolution of solid in liquid, my dear friends. And it's a type of a physical equilibrium only. Now my dear friends, before we look into this equilibrium, we must understand that what is a saturated solution. Saturation solution basically means a solution in which no more solute can be dissolved at a given temperature. Okay, what is that? Let us suppose if I will give you 1 liter of water and you keep on dissolving sugar into it. Keep on dissolving sugar into it at room temperature, let us suppose. A time will come that this water will tell you now you can't dissolve any more sugar into me because I am saturated. Yes or no? So the sugar, if you add little more sugar, that will stay at the base of the solution. You might have observed at homes also, if you keep on adding sugar to the water, then a time comes that some of the sugar will be visible at the base of the solution. You can see that. It means the solution has become saturated. But this process should be carried out at room temperature or at any constant temperature. Because why I am telling here, look here, at a given temperature, because if you change the temperature, solubility will also change. That's why the temperature has to be taken as what? Fixed, or it should be constant. So saturated solutions are made at constant temperatures or at particular temperature. And here I am preparing it as room temperature, my dear friends. Now, let us take on this saturated solution and understand our solute-solid equilibrium, my dear friends. Okay? Have a look here. I will write down here, if I take on a saturated solution. Okay? And now here I will take on undissolved solute. Now you will be thinking, what is that? You got a solution of sugar, let us suppose, correct? And that sugar solution is saturated, correct? And if you add little more sugar into it, will it dissolve or will not dissolve? That sugar will not dissolve. That means that will be your undissolved solute, my dear friends. And now what will happen, my dear friends? If it's a closed system, what is going to happen? The solute, this undissolved solute, will dissolve. But here is no space. So what to do? This guy wants to dissolve and it dissolves. But space is not there. So how does it dissolve? Have a look. Let us suppose in a classroom, okay, there are large number of students and the space within the classroom is completely occupied by the students. Yes, so classroom has become saturated. Okay, now one student has come late. He is waiting at the door of the classroom. Yes, and he wants to enter into the classroom. But classroom is already saturated. Yes, so my dear friends, how he will enter into the classroom? Because all the spaces are filled. There is a way. And what is that way? If he enters into the classroom, then one student has to come out, my dear friends. So that is called as equilibrium, my dear friends. Are you following my point? If 3 students are waiting at the door, those 3 students can enter only into the classroom when 3 students will come out. Yes? So remember, that means the rate of entering should be equal to the rate of leaving. In simple words, my dear friends. And understand one important point. The students who are waiting outside, okay, they are your undissolved solute. That is your sugar which is present at the base of the solution. Undissolved sugar. Yes? And this saturated solution is basically your classroom. So understand, there is an equilibrium between the classroom and the students which are outside. And what is that equilibrium? If 3 students are coming inside, the 3 students have to go outside. Yes? So that means the rate of entering should be equal to the rate of leaving. So this is exactly the equilibrium right out here, my dear friends. So solute-solid equilibrium is between the saturated solution versus the undissolved solute. And that undissolved solute is present as a sugar at the base of the, saturated solution. I hope you have understood, my dear friends. So now what happens? From this classroom, who is coming out? Students are coming out. Yes? What are students? They are solute only. Okay? And what is going inside into the classroom? The other students who are outside. So they are also just like solute. So I will tell, from this classroom, the students have to come out. So we will tell here that is called as rate of leaving. And that rate of leaving is basically called as rate of precipitation, yes, or also called as rate of crystallization. Let us suppose 3 students have come out. How many students will enter now inside, my dear friends? 3 students will enter inside. So it will be equal to rate of entering, and then when students enter into the saturated solution, they will also dissolve there. So we call it as rate of dissolution, my dear friends. So I hope you have understood. Take this as an example. Remember this as an example. Just a saturated classroom. Just an example. Saturated classroom. Okay. Take this undissolved solute as students at, or we can say at the door or by the door. Students by the door. Or you can say at the door. Yes? So my dear friends, from this saturated solution, from this classroom, 3 students are coming out and 3 students are waiting outside, they will enter. If 10 students are coming out, 10 will enter. If 1 student is coming out, 1 will enter. So when something comes out, remember, when, let us suppose, sugar comes out of the solution. Which solution? Saturated solution, sugar is coming out. Yes? Then the sugar which is outside at the base, undissolved sugar, should enter inside. Correct? So when sugar comes out of the solution, we call it as precipitation, rate of precipitation. Sugar is coming out of the saturated solution. And then some of the sugar is waiting outside, yes or no, at the base. Just like the students who are waiting at the, by the door. Then they will dissolve into the solution. Yes, some sugar is leaving, some sugar is entering. Some students are leaving, some students are entering. Some salt is leaving, some salt is entering. Yes or no? So obviously that will be called as rate of dissolution. I hope you have understood this particular factor, and it's between a saturated solution and undissolved solute. My dear friends, you can take an example of, let us suppose, a saturated solution of sugar you can take, yes, or you can take saturated solution of urea, or you can take saturated solution of, any other thing, let's suppose NaCl, sodium chloride, okay, and so there will be an equilibrium. So here I will write down undissolved solute. What is your solute now? Undissolved sugar, or it can be undissolved urea, or it can be undissolved NaCl, my dear friends. So this is exactly what is happening at the equilibrium. In one simple terminology, I will tell you that first of all you have to prepare a saturated solution. Okay? It's completely filled with the solute. Correct? Then you will add on little amount of solute from outside. Correct? What's going to happen? Will it dissolve? Yes, it will dissolve. But when something will precipitate out. When 3 students will enter, 3 students have to come out. So that will be the rate of precipitation. That means sugar is coming out of the saturated solution and some sugar is coming from outside and dissolve it into the sugar solution. That means precipitation is becoming equal to dissolution. 3 are leaving, 3 are entering. So, my dear friends, I hope you have understood it very well. And you can take saturated solution of sugar, urea and NaCl. And here on this side you have to use undissolved sugar or urea or NaCl, my dear friends. And this is nothing but solute molecules. Make note of this, please. Dear friends, now let us understand the equilibrium involving gas in liquid, my dear friends. It's a very simple thing, just similar to that of dissolution of solid in liquid, our previous topic. So it is exactly similar to that, only little bit change is there, little bit. So first of all, here we will understand Henry's law. So what is the meaning of Henry's law? Here we will understand. Okay. This law states that the mass of gas, okay, dissolved in a given amount of solvent at a given temperature is directly proportional to the pressure exerted by gas over the surface of solvent, or you can say liquid. So it's a very simple thing, my dear friends. If any gas has to dissolve, according to Henry's law, if any gas wants to dissolve in water, yes, or any other liquid, does not matter here, you can take any liquid. Let us take water only. If carbon dioxide gas wants to dissolve into water, okay, it is dissolution, okay, will depend upon what? The pressure which it will exert on the surface of water. If carbon dioxide gas will exert more pressure on the surface of water, then it will dissolve. So more dissolution will be there. So have a look here. This law states that the mass of gas dissolved in a given amount of solvent at a given temperature is directly proportional to the pressure exerted by the gas over the surface of solvent. If gas will exert more pressure on the surface of water, and then the dissolution will be more and more gas will dissolve in water. If gas will exert less pressure on the surface of water, less gas will dissolve in water. So dissolution of gas in liquid or in water depends upon the pressure exerted by the gas over the surface of that particular liquid, my dear friends. Please remember that. So what I am going to do here, okay? I am going to take a saturated gaseous solution. Saturated gaseous solution means a solution in which no more gas can be dissolved at a given temperature. So I will take on, let us suppose here, a saturated gaseous solution. A solution in which no more gas can be dissolved at a given temperature. Why you can't dissolve more gas? Because it is saturated. I have already told you about saturated solution. So I am taking here saturated gaseous solution. A solution in which no more gas can be dissolved at a given temperature. So what is this equilibrium all about? Let us try to understand, my dear friends. Have a look. Let us take a saturated gaseous solution. Yes? Do you remember the classroom, saturated classroom? Where everywhere students are there. There is no space. Just similar to that, my dear friends. Saturated gaseous solution. Okay? And obviously, did you remember that undissolved solute? Yes. And here the solute is not your NaCl, urea, because they are solid. Here your solute will be gas. So understand, it will be here undissolved gas. And obviously this undissolved gas is your solute here. Please try. So dear friends, now we will be just writing out here. This all is happening at equilibrium in a closed system. Here, what happens? If you have a saturated gaseous solution, just like a classroom, okay? That classroom is occupied by students, and saturated gaseous solution is occupied by what? Gas. Gas is a solute here. So if you want to dissolve more gas into this saturated gaseous solution, okay, or if you want students to enter into the classroom, let us suppose 3 students are outside and you want them to enter into the classroom, correct? But they cannot enter the classroom until or unless 3 students will come out of the classroom, because rate of entering should be equal to rate of leaving, right out there at equilibrium. That's a condition. So obviously this gaseous solution is already saturated. It's completely saturated. So if you want some more gas to dissolve into it, that gas is our undissolved gas, which is basically the gas which we are taking it from outside, and I want to dissolve it into this saturated gaseous solution. Correct? Does it have any space? No, it does not have any space. Then what is the funda? It's very simple, that if some amount of gas will dissolve into this saturated gaseous solution, then the same amount of gas should come out. That means, my dear friends, this saturated gaseous solution is your classroom. Then classroom should allow the 3 students to go out. And this guy should allow that some gas to go out. When some gas goes out, that is called as rate of evolution of gas. Rate of evolution of gas. In place of evolution, you can also write down liberation. Okay? So it will be equal to. Now the 3 students are waiting outside the classroom. Yes? Let us suppose if 0.1 ml of gas is coming out, then the same amount 0.1 ml of gas will go inside. 0.1 ml of gas is coming out from the saturated gaseous solution, then 0.1 ml of gas will go inside. Because it's outside, it's undissolved, so then it will enter inside. In the same way, 3 students are going out, 3 students are coming inside. Just like that, the rate of evolution or liberation of gas should be equal to. My dear friends, this has to dissolve. Rate of dissolution of gas. Okay, so rate of dissolution of gas in which solution, my dear friends? In saturated solution. In saturated solution. This is the rate of evolution of gas from saturated solution. So from saturated solution, gas is coming out, and then this undissolved gas which is outside will go and enter into the saturated solution. So rate of evolution of gas should be equal to the rate of dissolution of gas in saturated solution. So this thing will happen at equilibrium, my dear friends, and that's what we call as equilibrium involving gas in liquid. And how can you prepare a saturated gaseous solution? By following the Henry's law. Henry's law will tell you, if any gas will exert more pressure on the surface of a liquid, what will happen? Then more and more gas will dissolve in the water or liquid. Yes? Then the solution can become saturated. Once the solution becomes saturated, yes or no? Then you want to dissolve some more gas. That more gas is your undissolved gas. Try to understand. So you want to dissolve a little more gas into which solution? Into the saturated solution. Is it possible or not possible? Yes, it seems not possible, but it is possible. How? Because when 3 students will leave the classroom, then 3 will enter into the classroom. When 3 gaseous molecules will come out of the solution, then 3 will enter into the solution, my dear friends. Or when 3 ml of gas will come out of the solution, then 3 ml of gas will enter into the solution. So rate of evolution should become equal to the rate of dissolution of gas, my dear friends. And this is about the equilibrium involving gas in liquid. You can take an example of carbonated drinks also, my dear friends. In carbonated drinks like Coca-Cola, you have Mirinda, Fanta and all. What is present in those basically carbonated drinks? Carbon dioxide. Carbon dioxide is dissolved into water, and we are getting, carbonated drinks, my dear friends. And those bottles are closed, my dear friends. Correct? Let's do one thing first of all. Let us put more and more carbon dioxide into those bottles. Correct? Or in those water bottles. Let's put more and more carbon dioxide and make the solution saturated. Okay? Then I want to dissolve a little more carbon dioxide into them. Yes, it's possible only when the rate of dissolution will become equal to rate of evolution. My dear friends, I hope you have understood this thing. Please make note of this. So examples you can take like saturated solution of carbon dioxide gas, okay, will be in equilibrium with undissolved carbon dioxide gas in a closed system at equilibrium, my dear friends. So in place of carbon dioxide you can use any other gas as well, nitrogen, oxygen, whatever you like, my dear friends. Okay, make note of this. Dear friends, now let us talk about the characteristics of physical equilibrium. Our first point is it can be established in closed system, my dear friends. Why? The reason why we need closed system? There's a simple reason. The reason is that in closed system, matter can neither leave the system nor enter into the system. So my dear friends, matter cannot leave the closed system, yes, or some matter from surroundings cannot enter into the closed system. Then you will be thinking, what is the use of that? Use is very simple. If you keep an open system, if you have, liquid is changing into gas. Let us suppose, when liquid changes into the gas, what happens at equilibrium between liquid and gas or liquid and vapor? Liquid changes into vapor, vapor changes back into the liquid when there is a liquid vapor equilibrium in closed system. Let us suppose if liquid is changing into vapor and system is open, then what will happen? Vapors will run away from the system and there is no possibility of vapors changing back into the liquid. So equilibrium will not establish. So you have to use the closed system, my dear friends, so that when liquid will change into vapors, yes, then what will happen at equilibrium? The vapors can change back into the liquid. But if the system is open, the vapors will escape. Then there is no possibility of equilibrium. I hope you have understood, my dear friends. Let's go to the second point. At equilibrium, rate of forward process equals rate of backward. Obviously, let us suppose you have a liquid. Liquid was changing into vapors. Yes. And the vapor was changing back into the liquid. Correct? So here, liquid to vapor basically means here rate of evaporation. And that rate of evaporation is equal to rate of condensation. So obviously at equilibrium, rate of forward process equals rate of backward process. Okay? In a closed system. Equilibrium is dynamic in nature. This is important here. Dynamic means the equilibrium is in motion. Yes? Think that equilibrium does not stop. Let's talk about this dynamic term here. Let's talk about this dynamic term. Equilibrium is dynamic. Which means process does not stop at equilibrium, but takes place at equal rate or equal speed, but takes place at equal speed or rate in forward and backward directions. We are telling equilibrium is dynamic, that it's always moving, it's in motion. How can you tell that equilibrium is in motion? Yes, very simple. At equilibrium, what is happening? Reaction or process does not stop at equilibrium. Any physical process or any chemical reaction does not stop at equilibrium. Yes, what happens? It is moving in forward direction and simultaneously with the same speed it's moving in backward direction. So movement is there. So that movement is basically that dynamic term. It's moving in forward direction and backward direction, but at the equal speed. Yes or no, my dear friends? So net change is zero, but movement is there. But that movement is equal. in forward and backward direction. That's why the equilibrium is called as dynamic in nature. Yes or no? Remember, process, physical process or chemical reaction does not stop at equilibrium. It is moving, but it's not moving in one direction. It's moving in forward and backward direction. So movement is there. Correct? Let's go for the last term here. The measurable properties like temperature, pressure and concentrations become constant at equilibrium, my dear friends. So when any system, when any system achieves equilibrium, then these things will become constant. Temperature, pressure and the concentrations will become constant. Why? Because at equilibrium, the rate of forward process is equal to rate of backward process. So the net change is zero. When net change is zero, all the properties will remain constant. So obviously these temperature, pressure and concentrations will remain constant at equilibrium, my dear friends. And you can add on more points here, which we will add on in the chemical equilibrium topic and all. But here, one more point I would like to add on is delta G, change in Gibbs free energy. That will be obviously zero at equilibrium, my dear friends. I hope you have understood the physical equilibrium in a very beautiful way. Okay, let's meet in the next class with a new topic, which is chemical equilibrium, my dear friends. Till that time, take care of yourself. Yo-yo.